Come on in, everyone. Feel free to ask me questions while we're waiting for everybody else to come in.
I was wondering if you had like study guide material for like before our first exam.
Yeah, actually, I did find a mistake. I'm trying to remember if it was your class or not, but there was supposed to be one of my classes I marked today was a due date for a take-home test, but that's not the case. If that's what you're referring to, it'll be a week from today. But yeah, and today I'll put up the practice test, which is what I do every test we have. I give you at least 5 days with the practice test before the actual date of the test, the two.
I
Anything?
had a question. I
Go
had a
for it.
question about the last part of the lab.
Okay.
So at the very end, it's the one where it's actual practice. We have the
Mhm.
acceleration, theory, and then actual lab points.
Right.
I was confused about it says right click on one of the theory points, then choose format data series. Now click the paint bucket and then click on line, then solid line. Now click the marker and the marker options, then none. The
Mhm.
end result will be a solid line for theory points and markers circles for the data points. So it doesn't want a line of best fit for the theory points, and then just the like a kind of marker for the actual data.
Gotcha.
Is that
So
what
what
it's
kind
asking
of
for?
what kind of curve fit did you end up using? Did you use polynomial or linear or
I ended up using a power theory because it fit best
okay.
with all the data points,
Gotcha.
but I didn't finish it because I wasn't sure if that was what you were asking for.
Uh, I would have expected a polynomial. It's good to have that, so I would definitely keep that in there. The fact that you were taking the time to look at other curves is a good indicator that you know what the lab is supposed to be about. And I'll never take off points for you giving me extra attempts, extra graphs, extra data, extra pictures of graphs, that kind of thing. But I do think that one was supposed to be polynomial. I'd have to look to be sure, but it was a projectile type problem, wasn't it? That you were graphing?
Yes.
Yeah, so that should have been probably polynomial of second order. So make sure you at least include that one, and even if the other one fits better, you can just mention that, and that'll help you as well. But if you
Okay.
were to put that curve in there and not put the polynomial and not mention it, then you'd probably lose points because you didn't do what was supposed to be the normal expected curve fit.
Okay.
Okay.
Thank you.
That being said, I want to tell you guys I have now opened up Canvas for the lab. So a lot of you have already turned in lab one, and that's fine. But remember, I kept telling you these other parts were going to be due. Well, the problem was my bandwidth. Even though I had like 20 some 14-second and 11-second, 9-second videos, it took forever to get it done. I literally finished it this morning about 7 a.m. But they're now posted in that PHY 241 L01B Canvas course. And you look in week one, you'll see intro to lab, or excuse me, intro to yeah, it was intro to lab, but you'll see there's a new document that says with addendum. That is all the parts that I told you guys had to do in addition to it, and I moved the due date instead of it being this morning at 9 a.m. I moved it to a week from today at 9 a.m. So you should be able to do all that before next time. And if it is too much with you doing the Excel, which I don't think it is because Excel you normally do in the same day. But if it is, just let me know and I can give you a day or two extension if necessary. So hopefully everybody heard that. Anybody have any other questions? All right, so make sure you check in that. And if you know of anybody else in your lab that possibly is taking a different lecture than this one, please tell them because until they get put into that particular Canvas course, which they're not supposed to be in unless they're taking this lecture, then they don't know any of this information. That's why I sent it to everybody last night with all the emails that I sent to every class. Anybody have any other questions? All right. So if you do go over there and look, by the way, I'm going to read off what's over there for right now. So I have a week one, and you'll look, it says sig fig, scientific notation, units and dimensions. So that's one of my typical lectures I give on the first day, but it is related to lab. So I included that in there. I included the significant digit rules PDF because that's a lab thing. Sig figs when they fail, that's another video. Intro to SI, scientific notation standards. Electronic balance, that's a video that you're actually going to get data from. Then there's the introduction, measurement, and estimating. Again, that's a chapter one, but because it has measurement and estimating, that's somewhat of a lab related topic. So I included it on there. I also have a video link to how to read your calipers because we're using this style of caliper, which gets you 3 decimal places. If you don't know how to read it, this video should help you. And of course, you can ask me as well. Then you'll see there's all these videos. It says cylinder diameter 2, cylinder diameter 3, 4, 5. So that's me just measuring the diameter of the cylinder. Then there's 5 of them for me measuring the height. And I'm not making, I've made the measurements in the sense that I moved the object around to get all the different possible readings. And I did it with the calipers. I just filmed it for, like I said, 9 to 14 seconds. Your plan should be to open up each one of those videos and then pause it on a scene that you might find easy to read the measurement on, then you record that measurement in the data tables that I provided in the addendum portion of the lab. Then there's rectangular solids, the long measurement, the medium measurement, and the short measurement. Each of those have 5. And then there's a stainless steel sphere. Each of those has 5. And then you'll see lab one, introduction to lab with addendum. That's what you want to try to read. Now, I don't care if you turn that one or the other one in. It's just that that one explains a little bit more details of what I expected you to do with those rectangular solids and all that. I also put some graph paper on there. You might need that in lab in general, so it's nice to have. You definitely don't need it for this lab though. Okay. All right. It looks like I've got 21 of you. It's a pretty good number. So uh, we had homework that was supposed to be due yesterday. I just was being nice and decided to put it back a little bit. So you've got a little bit more time on that one if you haven't completed it yet. So hopefully you already completed chapter one homework, or excuse me, chapter two homework. No, it is chapter one. Sorry. Chapter two is going to go on now. We were able to do some stuff last time, and now I need to make sure I finish up my discussion of chapter two. So, anyone have any questions about any homework issues or anything like it? All right, I'm going to look at the notes from the 17th. Okay, so your class is the one where I got to derive v squared equals v0 squared plus 2a x minus x0. That's cool. I just wanted to make sure. That is not what I wanted. Okay. 122, 2024. Okay, there we are. All right. So first thing I want to start off with is I want to give you a typical problem. So last time I did a derivation in which there was a constant acceleration. And then I used some of the definitions to come up with an equation for velocity as a function of time. And then I used some more of the equations and it came up with the position as a function of time. That is the derivation of those kinematic equations that you'll be using the entire semester, or actually both semesters, and even 3 if you go somewhere and they require you to take a third semester of this, as a lot of places do. So it's the kinematics is not going away. That being said, a lot of people just skip the derivations. I try to do them so you'll know when they actually are applicable. So that's on there. But there's another reason that we actually show the derivations, and that's because there is such thing as a problem that you can solve that way. So let me start off by solving one of those such problems. Sorry, I'm sick too. That was another reason I ended up staying. Hopefully I'll be back Wednesday face to face. If not, I'll send you an email by Tuesday at 5. Hopefully I'll be there, but now I've gotten sick, so who knows. All right. Anyways, I'm going to share screen. Should come up in a second. I'm writing out a question right now that we're getting ready to solve. So you can record this too, or you can take a screenshot, whatever you want. If the acceleration of an object is given by a of t is equal to 3.0 t cubed plus 2.0 t minus 4.0, and the velocity is 1.4 meters per second at t equals 0, and the position is 1.0 meters at t equals 0.0 seconds as well. Okay. All right, I should say it this way. Then answer the following. So A, what are the units of the 3.0, 2.0, and negative 4.0? B, what is V of t? And C, what is X of t? So this is a very typical problem that you're expected to do. You'll see some like it in the practice test when you start taking that. What we're given here in this case, unlike last time where I said, hey, the acceleration is going to be a constant A, and then I ran with that and derived equations. I'm still going to do that same process, only now I'm doing it with A not being a constant. So here's our solution. Anybody have any questions on the wording of this or anything you don't understand about the question that you need to ask me about? Go for it. All right. So first off, what we have is A of t is equal to dv over dt. That's what we did before, except we had A of t being just A, which represented a constant. So in this case, it's going to be a little different. It's going to be, and notice I'm just dropping the decimal points and all that for convenience, 3t cubed plus 2t minus 4.0 is equal to dv dt. So that's where we're going to start off with, but we first have to answer part A. So part A, if you look at this and realize that 3t cubed plus 2t minus 4 is supposed to have units of meters per second, then you get that meters per second is equal to 3 question mark times t cubed plus 2 question mark times t minus 4 question mark. Okay, so that's what we're going to do to try to figure out what the units are. So the 3, since that whole term has to come out as meters per second, which you can also write, by the way. I don't want you saying it this way, but you can certainly write it this way. It's meters per second, like that. That's technically the same thing, but what I've found is that students can do a little better in their physics class in kinematics if they use the idea of the acceleration having units of meters per second every second, because otherwise students tend to get confused between velocity and acceleration. So I do recommend using that. But you see that meters per second squared is another way of saying that, and it's a lot easier to work with mathematically. But what we have in that first term is 3 times some units times seconds cubed has got to equal meters per second squared. So I think you can see that 3.0, oops. I think you can see that 3.0 is going to have meters per second to the 5th power. Two point zero would have to have units of meters per second to the 3rd power. And 4.0 would have units of just meters per second. Okay, so that's part of the answer. Everybody follow that? Did that make sense to everyone? All right, now we're going to go ahead with part B. So I'm going to take the integral of what I started, which is the integral of 3t cubed plus 2t minus 4 dt. In other words, I multiply both sides of the equation, and I mean this equation right here. I'm multiplying both sides of that equation by dt and then integrating. So on the right-hand side, I get the integral dv dt. And I think you can tell from this, we get basically 3/4 t to the 4th plus 2/2, which would be 1 t squared minus 4t plus a constant c1 is equal to v of t plus c2. Okay, that C1 and C2 are just integration constants, just something we had to do because we chose not to put limits of integration. I could have done integrals from 0 to t, which mathematicians don't generally like. You integrate into the variable that's being integrated over, but that's the way we do it fast and loose in physics. But you could have done that, and then you wouldn't have C1 of t and C2 of t. But hopefully, you know from especially your calculus class, but once you take differential equations, you'll even see a lot more herky-jerky stuff can happen with these constants. So I'm just going to combine them and make a new constant. What I'm going to do is I'll say v of t is equal to 3/4 t to the 4th plus t squared minus 4t plus a brand new constant I'll just call c. But we also know that v of t is supposed to be 1.4 meters per second is equal to 3/4 of 0 plus 0 squared minus 4 times 0 plus c. So you can see from that what c is going to be. So now we can say v of t is equal to 3/4 t to the 4th. And I could put a 4 up here. It was to the 0 power. That's why I didn't care too much about it. 3/4 t to the 4th plus t squared minus 4t and then plus 1.4. Okay. So we now have the velocity as a function of time. Anybody have any questions on that? Now we're going to do the same thing to get the velocity as a function of, or excuse me, to get the position as a function of
I have
time.
a question about part A.
Yes.
So if is time in that problem represented by per second? Because I don't understand how you got 3.0 meters per seconds to the fifth. Well, I understand, like it's seconds squared and then there's t to the third and then the exponents, but
Right.
how does it go? Is that what the unit for time is?
Yeah. Time has a unit of seconds. So I've got to be able to multiply 3 times seconds to the cube power. And the answer should come out in meters per second per second. And the only way we could do that is if we made it meters per second to the fifth.
Okay, I
That
understand.
makes
Thank
sense?
you.
No problem. Good question. Yeah, it's kind of a weird thing because you don't get to do work with units in your math classes in general. And in physics, they become really important in engineering as well. So it's it just seems a little weird when it first happens. You'll get used to it though. All right, so we know V of t is equal to that expression. So I'm going to write 3/4 t to the fourth plus t squared minus 4t plus 1.4. That's V of t, and we know V is equal to dx dt. So again, I'm going to multiply both sides by dt and integrate. So I will integrate 3/4 t to the fourth plus t squared minus 4t plus 1.4 dt is equal to the integral dx dt. And of course, hopefully you realize this, but when I do this right-hand side, that's just a fundamental theorem of calculus, which says the integral of a derivative is the original function. So I'll write here, fundamental theorem of calculus. Okay, same thing here. All right. So we've got that. Now I just have to integrate it. And of course, again, I'm not using a range of integration. So technically I would have to put constants. Just to show you how it's done, I'm going to go ahead and do a limit of integration. So I'm going to say from t equals 0 to t, and this side's going to be from t equals 0 to x of t, like that. This way I won't have a constant that I have to do a subsequent equation to verify. I just need to read the data up above. So when I integrate all this, I'm going to get integral of t to the fourth would be 1/5 t to the fifth. So this is going to become 3/20 t to the fifth plus 1/3 t cubed minus 2 t squared plus 1.4 t. And the other side, oh, I hate when it does that. Dang it, did it again. The other side's just going to be x of t, but in integrating from t equals 0, what I do know is that when t is equal to 0, x is supposed to be equal to 1.0 meters. So in reality, what I have to do is instead of putting 1.4 t and then hitting the equal sign, what I need to do is go ahead and add what x of t will be at t equals 0. In other words, I'm going to add to this plus 1.0 is equal to, in this case, it's just x of t. Now I could have done it that way, or, and let me show you this too. So everybody saw what I did there. That's one way of doing it. Another way of doing it is I could just leave it like that and know that when t equals 0, all this goes to 0, but when t is equal to t, I get all this stuff. The right-hand side, dang it, oh, aggravates crap. The right-hand side, however, is going to become x of t minus x of t equals 0. So that's x of 0. And that x of 0 is in fact the 1.0 meters that was given above. So you can see I would have gotten the same thing either way. And ultimately I get x of t is equal to 3/20 t to the 5th plus 1/3 t cubed minus 2t squared plus 1.4 t plus 1.0 like that. And that's it. Anybody have any questions on that?
I'm a little confused on how the limits work of setting a definite integral. Could you touch on that a little bit more?
Yeah, so what I did when I integrated under part C, where I've got the red t equals 0 and t, what I really did was wrote t to the 5th and then replace it with parentheses t minus 0. And then I did the same thing with t cubed, and then I did the same thing with t squared, and I did the same thing with t. That's where the range of integration is coming in. But you can see, because one of them is 0, you're going to get no terms from that. That's why the bottom integrating from t equals 0 gives you nothing. And all you get is the top range of integration, just giving you t's in the equation. Does that help you any?
Yeah, so you're effectively substituting t for t.
Exactly.
Okay, gotcha.
Yep. And I did substitute 0 for t as well, but that all disappeared. I just didn't take the time to show it. And that's
Right,
usually the
right.
part that confuses people. All right. Okay. Any questions on any of that? All right, so I want to recap what we found. I'm going to add some things that we didn't find. Your book does it, but it's not that big a deal. Basically, what we found is that V bar is just equal to delta x over delta t. And then V instantaneous is equal to the limit as delta t approaches 0 of delta x over delta t, which is really dx over dt. We also found S average is equal to distance traveled over time taken. Okay, notice I didn't take the time to write distance traveled and time taken. I just wrote distance and time, so that should be quite good, hopefully. So those are some expressions we got. The next level brought us to acceleration, and we found that the average acceleration is delta v over delta t. I should also mention that this is the displacement, just to remind you what you have to do with regards to that. And then A instantaneous, which I should be writing in blue, is equal to the limit as delta t approaches 0 of delta v over delta t, which equals dv dt, the derivative. From that, we were able to get some expressions like v is equal to v0 plus at, and that's for constant a. We were also able to get x is equal to 1/2 at squared plus v0t plus x0, which again is for constant a. We also got v squared is equal to v0 squared plus 2ax minus x0, again for constant a. Okay. There's one other equation, which you probably can make sense of yourself just by thinking about the graphs, but either way, I'm just going to put it here. V bar is also equal to V0 plus V1 over 2. Again, this is only true for constant acceleration. Okay. So what that means is if we're using these equations, we either got to go on the assumption that the acceleration is a constant, or that the fact that the acceleration is not constant is not such a big deal that it leads us to erroneous answers. Okay. So that's what we're doing with this. All of these, generally, everybody should have these memorized by the end of the semester just by working so many problems. That being said, I have an equation sheet that you guys will be using, and you'll see it first in the practice test when I post that sometime today or tomorrow. So anybody have any questions about that stuff? About those equations? We're going to use these over and over again. For instance, when we cover projectile motion and stuff like that, we'll be using them because nature is just giving us this great little gift about how nature behaves, where guess what? The acceleration an object gets is completely independent of the velocity it has. So, for instance, if you imagine dropping a ball from a great height, and let's say somewhere where the atmosphere, like on Mars, the atmosphere is almost non-existent. If you were able to drop a ball from a tall building, let's say on a Mars type planet, which has no atmosphere, but happens to be exactly the same mass and radius of the Earth, then we'd expect the exact same gravitational acceleration. And that acceleration is 9.80 meters per second every second. What that means is when you drop the ball, the instant it leaves your hand, it'll have zero velocity. And then 1 second later, the velocity is going to change by 9.80. It'll become 9.80 meters per second going down. Then if you wait another second, it's going to be twice that, or 19.4, 19.6, excuse me, meters per second after 2 seconds. And it's going to keep increasing by that exact same amount for as long as it falls, as long as we can ignore air resistance. Now, here's the weird part. If I instead of dropping the ball from the top of the building, if I instead stood on top of the building and threw the ball straight up at, let's say, 40 meters per second, then guess what? Gravity doesn't care. The velocity is going to change again by exactly 9.8. Only this time the velocity is initially going up. So you're going to end up getting 40 minus 9.8. So after 1 second, it'll be going 30.2 meters per second. After 2 seconds, it'll be going 20.4. After 3 seconds, it'll be going 10.6. That's what I mean by the acceleration acts on an object independent of what its motion is. So initially the motion was me just dropping it, and the velocity changed in the downward direction by increasing the velocity in the downward direction by 9.8 meters per second. In the second case, I threw the ball up, so an increase in the downward direction is a subtraction. So you end up getting negative 9.8. So that's really what we're looking at here. Anybody have any questions with that? I gotta make sure I got, yeah. Yeah, I got all the A equals constant equation. By the way, I said V0 plus V1. Your book says V plus V0, but to be honest with you, any two velocities is acceptable in that last equation. Okay. So let's say an example. An airplane. Whoa. must reach a speed of 30 kilometers, let's say 30 meters per second. 30.0 meters per second in order to take off. In other words, that's the speed at which it gets enough lift for it to actually leave the ground. The airplane also, also can accelerate at 1.90 meters per second every second. How long must the runway be? So there's our question. Anybody have any questions about that? Y'all understand it and everything? So what we're looking for is not how much time it takes for the object to reach the necessary speed, but specifically how much distance it must travel if I use that acceleration and I reach that final speed. So what I can write down right now is that the initial velocity, since we're talking about it taking off, the initial velocity is 0. So when you go to read a physics problem, you've got to read it a couple times, and you've got to not only get all the information they give you, you also got to get out the information that they sort of hinted at. Let's put it that way. So you've got to infer certain things, like when you're talking about an airplane taking off. Obviously, it took off from 0 initial velocity, more than likely. So v0 equals 0. We're also going to say the final velocity is the takeoff speed. So I'm going to say that's 30.0 meters per second. I know the acceleration A is equal to 1.90 meters per second every second. And again, that literally means we expect the object to have a constant acceleration, and that acceleration is going to change the speed by 1.90 meters per second each second it travels. And what we want to know is x equals question mark. And there's never a time you can't automatically set x0 equal to 0. So I'm going to go ahead and choose to set x0 equal to 0. Now, what physics is about initially when you first start doing this stuff is knowing your equations. So I wrote all those down up there. And knowing what all the symbols mean, what does T mean? What is A? What is D0? What is X0? What is plane V without anything on it? All those things come into play. And then part 3 of solving physics problems is looking for an equation that has the variables you have and gives you the variable that you don't have if you want. So right now, I'm looking for an equation that uses V0, A, X, and X0, which looks like this equation right here might be my huckleberry. If I may quote Val Kilmer, I'm your huckleberry. All right. So let's do that. So we're going to say V squared is equal to V0 squared plus 2AX minus X0. I'm going to plug this in and say 30.0 meters per second squared is equal to 0 squared plus 2 times 1.90 meters per second every second times x minus 0. So you can see we're actually solving for the x. That's what we want to know. So all I have to do is square the 30, which of course gives me 900. So I get 900 meters squared per second squared is equal to 3.80 meters per second times x. So now I'm just going to say x is 900 meters squared per second squared divided by 3.80 meters per second. So you see you're short basically, no, actually you have exactly the right number of seconds. 2 in the bottom and 2 in the top. Well, in the bottom of the top and 2 in the bottom of the bottom. And you're short 1 meter. So you've got a meter squared in the top that's going to cancel out one of those with the meter in the bottom. So you ultimately just get units of meters, which is exactly what we want for x. So I'm going to do 900, excuse me, divided by, and that gives me 236.8. So what that means, and by the way, we only had 3 sig figs, so I've carried 1 extra sig fig there. What that means is if the runway is not at least about 237 meters, the airplane's going to run off the runway before it lifts off the ground. Any questions on that one? Okay. What if I wanted to ask you for part B? So let's say part B. How long will it take for the plane to reach 30.0 meters per second? So that's a nice part B here. We'll just call this A since I did it sort of after the fact. Okay. So anybody have any idea how we might figure out the time? I should probably label these equations. Let's label this 1, 2, 3, 4, 5, 6, 7, 8, and 9, which would be IX. Okay, so which equation would y'all like to use since I've now numbered them to do part B? Anybody know? Let me turn on my chat because y'all might be typing. Nope, nobody typing.
Did
Yeah,
you use
6.
4?
Some people said 6, and you said 4 as well.
Wait, 6.
Okay, yeah, that is the easiest one. I expected everybody to choose 7, which works, but it's nasty and ugly, and you wouldn't want to do it. So really, the best one would be 6. So I'm going to say solution. V equals V0 plus AT. So you can do it like I just did, which is I plugged in all the numbers, or you can take this equation and solve it for the appropriate variable before putting in numbers. I'll go ahead this time and do it again like I did last time. I'm going to write 30.0 meters per second is equal to 0 plus 1.90 meters per second times t, and that gives me t is equal to 30.0 meters per second divided by 1.90 meters per second. And that gives me 15.78 seconds We only had 3 sig figs, so I really should put a mark there. But that's it. Anybody have any questions on that? Now here's the alternate way. I could have said V minus V0 is equal to AT, and then I'd say T is equal to V minus V0 over A, and just solve it that way. So T would equal 30.0 meters per second minus 0 over 1.90 meters per second. And of course, that would give me the exact same answer. Does that make sense to everyone? So don't get discouraged. That's one thing hopefully you're learning is a lot of problems have multiple ways you can solve them. So just if you see a classmate, they did a homework problem that you did and they use a different equation you did, that doesn't mean you're wrong. It doesn't mean the other person's wrong either. It might just be another way you can solve it. It's because in all honesty, what we do in the sciences is we look for as many ways to solve something as possible. So that gives you a little bit more confidence. If you talk about it generically on science in general, for instance, we like the fact that, using V equals V0 plus AT is one way of solving it, whereas X equals 1/2 AT squared plus V0T plus X0 is another way of solving it. And if I solved it both ways and got the same answer, I would be, really convinced that I was right. Because I did it 2 different ways and got the same answer. On a more general scale, though, that also reduces to something like what happened in 1905 when Einstein wrote like 6 or 7 papers, every one of which could have won the Nobel Prize, and one of them did, but it wasn't relativity, as a lot of people think. But what happened there was basically we already had an issue coming up. In other words, the science of biology and the science of geology were both starting to bump heads against our traditional knowledge of the universe. Specifically, our book of record was the Bible, the Old Testament. And if you go through and add up the begats and the ages, you can actually work out exactly how long ago before King Nebuchadnezzar walked the surface of the earth, how long before that was the day that the earth was made according to Genesis. And when you do that, you get on the order of a couple thousand years. Okay. And that was fine because a guy by the name of Lord Kelvin had already calculated that if the sun was the most efficient power source, was running on the most efficient power source that we knew of at the time, which was just basically a lump of coal. If the sun was in fact made of a lump of coal, then Lord Kelvin showed that could probably last 10 to 50,000 years. So everything was pretty good with that. But in the meantime, Lyell and various other scientists in other fields as well started reaching conclusions that perhaps, just maybe, the planet used to have a different configuration of continents on its surface. Because we'd find fossils of very, very, very similar species on South America, the part that juts out to the east, and Africa, the part which Africa kind of looks like a head is one way of thinking about it. It's basically the back of the skull all the way down to the chin. And if you go into the back of the skull area, that's roughly where that jutting out part of South America fits into Africa. And they did, in fact, find species and fossils very similar to each other on both sides. In other words, South America had very similar fossils to Africa. And one of the ways you explain that is maybe those two were connected initially. However, they knew that that implied that the Earth might be hundreds of thousands of years old. That would be a problem, according to Lord Kelvin, because Lord Kelvin said we could, last somewhere between 10 and 50,000 years. However, we also started finding out that species seemed to change. They had metamorphoses from one generation to the next in such a way that one species can become an entirely different species over a period of time. So that left us with a big question. 2 of our sciences were pointing to the Earth being a lot older than it could be based on the sun being made of coal. So Einstein had published his special theory of relativity. So sorry about that. And literally, he sent it in the next day as like an appendix. Oh, by the way, I found this E equals MC squared. That E equals MC squared was the equation that we needed to make sense of how the sun could live that long. So we now know the sun will likely live on the order of 10 billion years, and that fits perfectly well with plate tectonics as well as evolution. So that's something nice to do and something to keep your eye on. When you're in one science, the more sciences you have pointing to the right answer, the better you are and the more confident you are about that result. Same thing within a science with multiple equations and multiple ways of doing it. Your book has a pretty good problem on well, it has a section on solving problems, but it has a pretty good problem on dealing with airbags in a car. It does other things like how long does it take a 4 meter long car to cross 26.0 meters wide intersection after the light turns green if the car accelerates from rest at a constant 2.0 meters per second every second. The car has to travel 26.0 meters plus the 4 meters of its length, which is equal to 30 meters to do that. So that's another very straightforward problem. It's a good example. Your book uses it as the first one to show them implementing the problem solving strategy that they're giving you in section 2.6. So definitely read over that. I think there are plenty good and plenty of examples in there, but I need to go on to the other stuff as well. So the next part that we have to do is now that I've shown you how to use that, and there's plenty of videos online. I've given you links to them in Canvas, videos where I solve projectile motion or where I solve kinematic equations, not unlike these. So you can certainly look at those as well as the ones in the book. But what I'm wanting to go to is what Galileo discovered. So Galileo basically faced the Inquisition. Actually, if I remember correctly, it was like January 30th of 1630 or something like that. So the anniversary of that trial is coming up pretty soon. It might even be the 24th or something, but either way, so he had basically read about someone making a telescope, a guy by the name of Hans Lippershey, and he used that to make his own telescope. That guy basically just used it to sort of look at things nearby, whereas Galileo and possibly one other person were the first person to actually make a telescope and use it to look at the heavens. The other person was in the uh, Manio colony that we know of as the sequel to the Lost Colony. So there was a scientist there. I think his name was Thomas Harriot, and he did the same thing, but he was in the backwater, so he didn't publish his work, didn't get his work until he got back from the New World. So we didn't know that for some time, but it seems like he might have beat Galileo to looking at the heavens. But when Galileo looked at the heavens, he saw one thing that he thought was a nail in the coffin for the Ptolemaic model, which had a heliocentric, or excuse me, which had a geocentric model of the universe. He specifically saw that Jupiter had satellites. Jupiter had, in fact, four. He called them the Medicean moons because the Medici family was very powerful, and he knew he'd get a lot of reward for that. So he named them the Medicean moons, and it's Io, Europa, Ganymede, and Callisto, and every model always showed Jupiter was moving. So that really put a problem in. Specifically, at the time, we were using Aristotelian physics, and Aristotelian physics was based on the idea that things naturally come to rest. There's two types of motion. There's violent motion, which has to be sustained by a force, and then there's natural motion, which is where an object tries to go back to the origin of its element. So earth, wind, fire, and water, you're familiar with. Maybe Mila Jovovich is the fifth element, the quintessence, which is the heavens. If you're one of the 8 people that saw that Bruce Willis movie, but anyways, basically the rule was anything made of wind would have a natural place above the Earth's surface. Therefore, if something had wind in it, it would naturally fly. If something had earth in it, it would naturally fall towards the center of the Earth. And yes, they knew the Earth was spherical at that time as well. So that was the motion. Any other motion, like if you wanted to make a bowling ball, which assume it's a bowling ball made out of wood so they could make sense of it, then that sort of earth type material, if you wanted to make it roll, you actually had to apply a force to it and keep applying a force or it's going to come to a stop. So the idea was, for instance, if a bird happened to be sitting on a tree limb and looks down and sees a worm, if he were to let himself jump off of the tree limb and fly down to get the worm, if the Earth was actually orbiting around the sun, the poor bird would be left behind. That was their idea. So we knew from Galileo's observations of the moons of Jupiter that that wasn't happening in that case. So he went to study motion in general, which was good because he was forbidden from studying astronomy anymore. So what he ended up doing was he realized he couldn't measure uh, motion very well in falling because it happened so fast and they didn't have a really good instrument. So you couldn't like just look at a pin and say, look, the pin fell. I don't know if that sped up, slowed down, went the same speed constantly or whatever, but he realized that if he did it on a gradual inclined plane, he could relate the ratio of that to say the other parts of the triangle to the actual acceleration due to gravity. And what he discovered was that all objects fall at the same rate, and that rate is 9.8 meters per second every second. So Galileo was the one to discover that, and basically, it's supposedly the fact that he went to Pisa and dropped two objects at the same time. We don't have the red tape that would be required for to do that. Even during his time period, they had a very big bureaucracy. So we would have expected some very serious documentation of him being allowed to go into the Leaning Tower of Pisa to do that. We've never found anything like that. So we think it's an apocryphal story. Not only that, that's high enough where the velocities would screw it up and you'd probably get a null type result where the two would be different by a little bit. And that would be a problem as well. So anyways, we don't believe that part of it's true, but he was right. And when we learn Newton's second law, we'll know exactly why. So what Galileo said was all objects accelerate at the same rate when they're accelerating due to gravity, and that the acceleration due to gravity is A. Ooh, I lost my glasses. I'm looking all over for my glasses. The acceleration due to gravity is A, which we call G, which is 9.80 meters per second every second, which is also about 32.2 feet per second every second. So if you want an idea how fast that is, it is faster, more fast than Usain Bolt. And I forgot, I'm sorry, I should know. I think a Canadian ended up beating Usain Bolt's record. So I should probably update my stats to include that nice Canadian guy, but I haven't. So anyways, Usain Bolt's still pretty fast. But what happens is Usain Bolt takes off and his acceleration is greater than 9.8 initially. But by the time he gets 30 or 40 meters in, gravity has completely surpassed him and blows him away. So it's pretty fast. And hopefully by seeing it as 32 feet per second, you realize how fast it is because most people aren't that good. Most Americans aren't that good at understanding meters versus feet. So that's what the big deal is. So let's look at a problem like this. So here's an example. If an object is dropped from a great height above Earth and air resistance is negligible, what would the object's speed be after, whoa, 0.50 seconds, 1.0 seconds, 2.0 seconds, 3.0 seconds, and 4.0 seconds. Part B, how far would it have traveled? At each of those times. Okay. So that's your two questions. A, what would its velocity be at those various times? And B, how far will it have traveled? So here's my solution. So what we have is V0 is equal to 0. V is what we're looking for, and this is all about part A, so I'll put that there. Okay, and T is equal to 0.5 seconds. 1, 2, 3, and 4. Well, we can look back at our equations, and the best bet for me looks like equation 6 again. Y'all agree with that? VI, equation VI. So what we'll say is V equals V0 plus AT implies V at 0.50 seconds is equal to 0 plus 9.80 meters per second times 0.50 seconds. And obviously, that's going to be 4.9 meters per second, and it's downward. So since I'm solving for V, that's a velocity, which is a vector quantity. So I'm supposed to say downward. All of them are going to be downward. So now if I wanted to do the next one, I'd say V of 1.0 seconds is equal to 0 plus 9.80 meters per second every second times 1.0 seconds. So that's going to give me 9.8 meters per second. V at 2.0 seconds is 0 plus 9.80 times 2.0. Notice I dropped the units. It's better to keep the units while you're going, but I've shown you enough of that, so it's not too terribly bad. So this is going to be 19.6, which technically I'm not supposed to have that third sig fig, but I'm going to just write it down anyways. Meters per second at 2.0 seconds. V of 3.0 seconds is equal to 0 plus 9.80 times 3.0. 3 times 9 is 27. 3 times 8 is 24, so that'd be 29.4. Again, carrying one extra sig fig. And that's at 3 seconds. And then finally, V of 4.0 seconds is equal to 0 plus 9.80 times 4.0 seconds. So that's really 19.6 plus 19.6, which is about 40 minus 0.8. So that'd be 39.2 meters per second at 4.0 seconds. Any questions on that one? Great. My nose is running, about to kill me. No questions on that one? All right, now we'll look at, notice by the way that basically the time and the velocity are directly related. So if I double the time, I double the velocity. If I triple the time, I triple the velocity, that sort of thing. So that's something that can come in handy when you're trying to just rapidly estimate these solutions and to check your work. Now I'm going to do part B, whereas we want to know how far it is. Well, the equation I'm going to use in this case is actually equation 7, and that is x is equal to 1/2 at squared plus v0t plus x0. I'm going to go with a equals positive 9.80. By calling it positive 9.80, that means downward is the positive direction. And that's why those velocities came out as positive as well. So A is positive 9.8 meters per second per second. Once I've established that that's positive, then I have to stick with that. So anything comes out negative must be going up, all sorts of crazy stuff like that. V0, we dropped it, so that's 0. X0, we can always set the origin wherever we want, so I'm going to call that 0. So I'm going to say x of 0.5 seconds is 1/2 9.80 meters per second times 0.50 seconds. That's going to be squared. So 4.9 times 0.5 times 0.5 gives me 1.225 meters. That's obviously way more sig figs than I was allowed, but you get the point. Let me go ahead and box off these answers. So we got this one. So if I go to x equals 1 second, notice I'm doubling the time, but in this case, the distance goes like time squared. So I should multiply the time by 4. And 4 times 1.225 is, of course, 4.9. So you say x, we'll say x of 1.0 seconds is 1/2 of 9.80 meters per second times 1.0 seconds squared. That's obviously half of 9.8, which is 4.90 meters. I can do it again. X of 2.0 seconds is 1/2 9.80 meters per second to 2.0 seconds. So I just doubled the time again. So I expect this to go up by a factor of 4. And in fact, 0.5 times 9.8 times 2 times 2 gives me 19.6 meters again. And now I can do x of 3.0. I'm going to drop the time, the units this time. This time I tripled it since I did the 1 second, so it should go up by a factor of 9. 9 times 4.9 would be 36 plus 8.1. That'd be 44.1. So let's check it out. 0.5 times 9.8 times 3 times 3. 44.1 it is. And then finally, we'll do the 4-second mark. I think that was the last one. So x of 4.0 seconds is 1/2 9.80 times 4.0 squared. That's double the 2-second one, so I'd expect it to be 4 times 19.6, which would be what, 80 minus 1.6, that'd be 78.4, something like that. So 0.5 times 9.8 times 4 times 4, 78.4 it is. Any questions on that?
I did have a question.
Yes.
So you said that it's going downward for part A. That doesn't mean like so since we started from the top, it going downward is still positive, right?
Yes.
Okay.
What forced it was the second I wrote 9.8 was positive.
Right.
Good question. Yeah, that's sort of the trick to this. That's the thing that makes it a little hard for students is they're just not used to thinking in terms of units and coordinate systems and all that stuff. But basically, once you decide uh, to use a equation, you should probably think about a coordinate system and then choose whether you're going to call up positive or down positive. And there's a lot of times calling down positive is just more helpful. So feel free to do that. You're never going to be wrong. You'll just get, a different answer by a sign. All right. How do you think that would differ if we threw a ball upwards? So a ball, this is another example. A ball is thrown upward at 29.4 meters per second in a place where air resistance can be ignored. Okay, so we're throwing a ball up at 29.4 in a place where air resistance can be ignored. So part A, how high will it reach? B, how fast will it be going at t equals 1.00 seconds, 2.00 seconds, 3.00 seconds, 4.00 seconds, 5.00 seconds, and 6.00 seconds. And then part C, how high will it be at those times? Okay. So that's our big question. I'm going to start with A, which is how high will it reach? Well, when you throw a ball up, what can you tell me about it when it reaches its max height? You tell me anything about its motion at that point?
Velocity and acceleration.
Guinevere, did you try to answer?
Yeah, can you hear me?
Yeah, I couldn't hear your words, but I do hear you now.
I guess it loses acceleration. Acceleration goes to zero when it reaches its maximum point.
Yes. So I think I heard everything you said, but yes, that's exactly the point. When you throw a ball up, it slows down according to, remember I told you how the acceleration is not going to change based on the motion. So it's going to slow down or attempt to slow down by 9.8 meters per second each second. Once it gets to the top, it should reach a zero velocity because if it still had some positive velocity, it would still go higher. If it had some negative velocity, it came from higher. So yeah, the final velocity must be zero. So I'm going to say V equals, well, I don't want to say that one actually. I could do that. Yeah, I'm going to say V squared is equal to V0 squared plus 2AX minus X0. And I'm going to take the initial height to be 0. I'm going to take the acceleration to be pointing downward. and I'm going to call downward the negative direction. So I'm going to say that's negative 9.8 meters per second every second. And I'm going to say V0 is positive 29.4 meters per second. So I can solve for X, and that'll tell me how far it's gone. I do know that V is equal to 0. So putting all this in, I get 0 squared is equal to 29.4 meters per second squared plus 2 times negative 9.80 meters per second times just plain X, which is what we're looking for. You can see that the negative 9.8 will make that whole term become negative. So we can ultimately just say that X is going to be 29.4 meters per second quantity squared over 2 times 9.80 meters per second per second. So you can see that's going to be meters squared per second squared divided by meters per second squared. So it does come out in meters like we expect. So if I do 29.4 and I square that, and then I divide it by parenthesis 2 times 9.8, I get 44.1 meters. Does that make sense to everyone? Bonus. How long did it take to reach the 44.1 meter height? Anybody want to guess at that one? It's something that you could probably do in your head. Anyone? Okay. Remember what I said, the velocity or the acceleration. It's actually easier than that, Michael. The acceleration acts independently of the motion. So the acceleration is going to consistently decrease the velocity by 9.8 every second until it reaches 0. If you notice, 29.4 happens to be 3 times 9.8. So we can say 29.4 equals 3 times 9.80. Therefore, t would equal 3.00 seconds. So you could also do that by saying v equals v0 plus at. Solving for t, you gave v minus v0 over a. Of course, the final velocity is 0. The initial velocity is 29.4 meters per second, and the acceleration, notice the negative. I have to use it there. Meters per second per second. And lo and behold, you're going to get 3.00 seconds. So that would give you how much time it would take. And then you could use x equals 1/2 at squared plus v0t plus x0. You could use that to find the 44.1, and you'd get x is equal to 1/2 negative 9.80 meters per second times 3.00 seconds squared plus 29.4 meters per second times 3.00 seconds. And lo and behold, that'll give you 44.1 meters as well. All right, let's do part B now. Anybody have any questions on that before we go to B? We only got a couple minutes left anyways. So it's saying how fast will it be going at t equal 1, so on and so forth. What we know is the velocity is going to decrease by 9.8 each second. So I can work this out without even thinking about the equations, but you should be able to use the equation as well. We know that, for instance, V of 0 is positive 29.4 meters per second. V of 1.00 seconds would be 29.4 minus 9.80, which 29.4 minus 9.8 gives me 19.6 meters per second. V of 2.00 seconds would be 29.4 minus, well, actually, I can just go from the last one. I could either do 2 times 9.80 like that, or I could just do 19.6 minus 9.80. And both of those, I get 9.8 meters per second. Again, you could also use, like I said, V equals V0 plus AT. That works fine. But I want you to sort of understand acceleration and the way it behaves. And that's what this showing you this way is hopefully doing. So this one could be 29.4 minus 3 times 9.80, or it could be 9.80 minus 9.80 equals 0.00 meters per second. And that's exactly what we expected, because we found out that it would take 3 seconds to get to the top. If I do V of 4, so now the last velocity was 0, but I need to subtract from it 9.8. So I'm going to say 0.00 minus 9.80 gives me negative 9.80 meters per second. That means it's now going downward at 9.8 meters per second. If I do V of 5.00 seconds, I get negative 9.80 minus 9.80 meters per second. Actually, I won't even write the meters per second yet. I'll go ahead and do the math and then write the units on the end. That's negative 19.6 meters per second there. And finally, V of 6 is equal to negative 19.6 meters per second minus 9.80 meters per second gives me negative 29.4 meters per second, which is exactly the reason that it's not very smart to shoot a gun straight up in the air. Obviously, air resistance matters, but would you be interested in wearing a life preserver as a Kevlar vest instead of an actual Kevlar vest? Because that's what you're doing. You're relying on air resistance to stop the bullet from killing you if you shoot straight up and it happens to hit you. So, anyways, that is a good representation of how acceleration behaves. Time's up. You guys are free to go. We have completely finished chapter 2, so we'll go into chapter 3 next time.
Wait, I have
Thanks.
a cool question.
Yeah, go ahead, Joy.
So when you were solving for V0 to V3, you started with, the initial velocity at 29.4, but then when you did 4, 5, and 6, why did you change it to?
What I was trying to show you was that the idea of constant acceleration means the velocity is going to change by the same amount every time. So I could go all the way to 29.4 and then subtract some number of seconds times 9.8, or I can just subtract 9.8 from the last one. So that's why I started switching, because it's so much easier to just subtract 9.8 from the last.
Oh, so you could hypothetically do that with any of these. You don't have to, okay, I see.
Yeah. Yeah, it's weird in that I'm trying not to use equations, but I am using equations. Mainly, I want you to understand what constant acceleration means. It means the same velocity is going to change, or the velocity is going to change by the same amount each time unit. So if the time is 1 second, it's going to be 9.8. If the time is half a second, it's going to be 4.9, so on and so forth. Anybody else? So do take the time to check out my YouTube videos on acceleration and kinematic equations and stuff like that. I put several links in your week 2 module, so it shouldn't be a problem for you finding it. And of course, you can look for other places too, but
Yeah.
you definitely use the books. Anybody else have any questions?
I had a question about like our exams and everything. So I looked at the syllabus, and I probably just forgot from like the first couple days of class where we talked about the syllabus.
Mhm.
But we're having our first exam online.
Right.
What do we? Is there like a specific program that we have to use for that?
Okay, so no, you're actually just going to go into Canvas. Where you have week 1, week 2, week 3, all that stuff. There's going to be a module before you get to week 1. It'll say online tests. There'll be another one before
So
that that says practice tests, and that's where you're going to go, and you're just going to use Canvas.
are the midterms and the final like that, or are
Uh,
those in person?
they are in person, but they're often still done on the computer. But you'll have a lockdown browser, and people will be watching you. Whereas this one, you're allowed to look.
Okay.
You're doing the online test. You're allowed to do Google searches and that sort of thing.
All right. Thank you.
You're welcome, George.
Are we gonna be on Zoom next week or in person?
Uh, Definitely next week. I cannot imagine a scenario unless I get deathly ill or something. I can't imagine a scenario in which I wouldn't be back next week. I still think I'm going to be back Wednesday. So hopefully we'll get out of that then.
Okay. All right. Thank you.
Thanks, Eddie.
Hope you feel
Like I
better.
said, I'll let you guys know well before 5 o'clock on Tuesday if I end up not making it in on Wednesday.
Okay. Hope you feel better.
Thank you, Eddie. Anyone else?
I have a question about Lab 1.
Yes.
So I know the due date's extended and everything.
Right.
I don't have a meter stick at home. Is it okay if I use like a tape measure and like do the unit conversions for the half G lab?
Honestly, what I would prefer you to do is either just use a ruler, like walk into a Home Depot or walk into a food line that has a ruler in centimeters and use that and just put it right back when you're done. We did ask you to have a ruler and protractor, so that might be worthwhile to buy anyways. But I wouldn't do the conversion just because the conversion leads into problems with regards to sig figs and all that stuff. So yeah. If not, we have some that you can borrow from the lab too, so I can also help you that way.
Okay, cool. So we'll talk
Right?
about that
Yeah.
Wednesday.
Anybody else? I did mention too, you probably, when you're measuring circumference, it's really hard to measure circumference. So what I would do is take like a piece of string or a little strip of paper and wrap it around the circumference and then make a mark where the two overlap and then measure that distance to that mark. And that'll be in centimeters, that'll be your circumference. That's a better way to do that, right? As opposed to like taking a tape measure and trying to roll it around and stuff.
Totally. All right. Thank you so much. Have a good one.
You're welcome. See you, Michael.
I've got
Anybody
a
else?
question for lab one as well.
Yes.
So I've submitted my first one
Mhm.
through the lecture course, I think.
Right.
Do you and then you've added on, there's more for the lab course?
Yeah, that stuff that I kept telling you I was going to get, but I had a hard time getting that came on now. So you can just take and add it straight into the document that you already turned into me and then turn it in again on the lab site. That would be great. Uh, or you can start over from scratch, whichever one you want.
Okay, so you would like it on the lab course submission, not the lecture one.
Yeah, I can always get it. The main thing is, I'm probably going to be giving you guys bonuses that turned it in early. like that. So I'll probably give you a couple points bonus for being over there. But yeah, if you just submit it at the 241.L01B course, that would be better.
All right, thank you.
You're welcome, Jude. Anyone else? And looks like that's it. Bye, everyone.